Hello, a very good afternoon to all of you. So, today's among this very tense situation over here, keep care of yourself, use sanitizers, and keep wear mask whenever you are going out. And most of the time, it's an examination time, so study hard. Yesterday's, I'll start with the continuation of my yesterday's lecture, wherein I had promised you I'll be delivering on the design of tubes and the problems associated with the tanks and the tube design. So, here are some crucial factors before we move into the numerical part of it, because my idea is you should always know the emotion behind the action, because if you know the emotion, you really know the story, then you can solve any problem. But if you are learning a concept by just solving problem, and an examiner twists a problem here and there, you will mess up. So let's start with design of tanks with tubes. So basically what we are having is, we are having tanks and we are having tube arrangement. So usually, yesterday also we have seen the tubes are only carrying oil, and they are used for cooling of the transformer purposes, and the energy which they are and the process which they follow is of convection, whereas in the tanks they follow both your radiation and convection. So the dimension of the tank depends upon the type and capacity of transformer, voltage rating, and electrical clearance to be provided between the transformer and the tank. So there is some clearance, so they should not short circuit themselves. So there has to be some clearance between the tank and the tube. So wherein here there is a very good arrangement in this book, you can see over here. So this arrangement, there's the total height of the tank, and this is, you can see the D, this is the distance between, this is three phase transformer arrangement, 1 2 3. So these are like one limb, two limb, three limb. So distance between adjacent limb here, and it's given as D. And you can have your CW, this is that CW, this is the width clearance between the outer winding and the tank wall. So between the outer winding of the transformer and the tank wall, this is some clearance. Similarly, here you can see there is one more factor associated with it, that is your CH. This is the height wise clearance between the tank and the wall. And here you can see there is another association of this is your total width of the window, and this is the total height, and this is the dimension. And similarly, you have associated with it some other factors, that is CW, that is width clearance between C. Similarly, width clearance between the outer ring, and CL is the length wise clearance between the tank wall and the outer ring. And CH, that is CL, here is CL, this is the lengthwise clearance between the tank wall and the outer winding, whereas CH is the height wise clearance between the tank wall and the outer winding. And DE is the external diameter of the outer winding. So DE would be somewhere here. Here they are missed in this particular diagram. So usually what we have is, in the yesterday's class also, what we followed, if you will look at our yesterday's class, if you go back to that class, we calculated a particular formula, and that formula for calculating the number of tubes reflected like this. That was, our NT was equal to total area of tubes divided by area of it. Total area of what? Not the total area of, total surface area dissipated by the tank and the tubes, and divided by area of one particular tube. So the height wise clearance includes the clearance of 50 to 60 millimeter at the base, clearance of 150 to 250 millimeter above, and oil and space of about 200 to 250 millimeter for leads. Now we will just directly move to the problem, and we can very easily relate a problem. Let's go to one of our problems, and let's see how can we relate with this particular problem. How do we go about this problem? So the problem reads, the full load efficiency of a 200 kVA the full load efficiency of a 200 kVA transformer is 98.2%. The full load efficiency of a 98 kVA transformer is this will be doing next. First we'll go to this design problem, because that other part of the problem is very easy. First let's understand the design problem. So I think it's clear. Yeah, so we'll be moving to this design problem, and we'll see. So the problem states, design a suitable cooling system for a 500 kVA 600. This is your primary and this is your secondary. You can say this is my low voltage and high voltage also. This is high voltage HV, because this is 6600, and this is low voltage LV, because this is 400. 50 hertz 3-phase transformer with a total full load loss of 7 kilowatt. The transformer main dimensions are 1 meter in height, 0.96 meter in length, and 0.47 meter in breadth. Use cooling tubes of diameter. So here he is giving use cooling tubes of diameter breadth. Use cooling tubes of diameter 50 mm to limit the average temperature rise to 35 degrees Celsius. Use clearance of 50, 14 and 13 centimeter on height, length and width. Use 135 centimeter as the length of cooling tube. If the length of cooling tube is not given, we can approximate it 0.9 into height of tank. Whereas height of tank here it is given, where it is given in the main 1 meter plus some clearance is there. So first, whenever we are approaching a problem in the classroom also, I have told you how do we approach a problem. It's as simple as that. We'll first take the data. What is the data given? Before approaching a problem, the best approach according to me would be to read the problem once or twice and then move to the problem. So number one thing is the transformer rating. So we know the Q of transformer is how much? 500 kVA. It is given over here, 500 kVA, and it is a 3-phase transformer. Okay, we are interested in this. So here in this problem, okay, we have also this turns ratio also. We can write turns ratio is 600, this divided by 400 volt. So this is your HV by LV. This is also given. No problem, we'll take down the data and we will see what data we have to utilize. So we can write this as our voltage rating. Voltage rating is 6600 by 440 volts. This is 440 volts. And our tank size, now our tank size, how much is given? The length into height into breadth. This is 1 meter into 0.96 into 0.47. If I write my tank size, I can write it is 1 into 0.96 into 0.47 meter. This is given. Another thing is for us which is given is that clearance is given. Clearance is given 50 into 14 into 13 centimeter. Now please, one important factor which we have to keep into consideration is the unit. Here we see the unit is meter, here we see the unit is centimeter. Another thing, diameter of the cooling tube is given. Now diameter of the cooling tube, how much it is? It is given 50 millimeter. You from here only you can see. Use clearance 50, 14, 13, length and width size. Use 130. Here it is, but here you see use cooling tube of diameter 50 mm. So 50 millimeter. Now what? Another thing, allowable temperature. That is your temperature. Theta is given 35 degrees Celsius. Now if we want the total size of the transformer including clearance of on all sides, so we have to include the clearance of all sides. To include the clearance of all sides, what we will do, I'll move to the next page. to include the clearance of all sides, we have to take into consideration the clearance that is previously given. So to include, I will write here only for your better understanding. To include the clearance, we have to use clearance where it is given. Here it is given 50, 14 and 13. 50 centimeter, 14 and 13. This is in meter. So 50 centimeter in meter, it would be 0.50 meter, and that would be, if we, it is easier, let's, for suppose we convert that meter into centimeter. So we'll see clearance is, now if we want the height of st of the transformer, that is 1 meter. So we can write 1 meter as 100 centimeter plus clearance is 50 centimeter. So total height would be 150 centimeter. What I have done, I have written meter in term of 1 meter is equal to 100 centimeter. That's it. And now another thing is that the length of that wire, length of that dimension is length is given as you see here 0.96 meter. So 0.96 meter can be written as 96 centimeter, and plus how much is the clearance, 14 centimeters. So now your new length would be 110 centimeters. Now the width is given as 0.47, width is given as 0.47. In centimeter it would be 47 centimeter, and clearance is 13 centimeter. So this would be your 60 centimeter. So now the new thing which we are having is total size of the transformer including clearance. I can write total size of the transformer including clearance. How much is it? Total size of the transformer, it would be your so what do I say, your height into your length into your height into your length into your width. So you just saw now that it became 150 and your length became 110 and this became 60 centimeters. So this is the case, this is 100, 110 and 60. Now you tell me, in yesterday's class we have seen a formula for total dissipating surface neglecting top and bottom surfaces. So tell me the formula from the yesterday's class. Total dissipating surface neglecting the top and bottom surfaces. So simple mensuration, it was twice height into length plus height into width. So you can calculate, you know your height is how much, 150, your length is 110, this is your 60. So you can write twice. So now 150 centimeter, if you want to write 1 meter is equal to 100 centimeters. So your 1 centimeter is equal to 10 power minus 2 meter. So your 150 would become how much meters? 1.5 meters. Similarly, this will be divided by 100, 100 and 100. So this is your 1.5 and your length would be how much? 1.1. Similarly, here your height is again 1.5 and your width is 0.6. So if you do the mathematics, you will arrive at this 6 5s are 31. See here also you can do 6, this is 0.9 and 1, this will come around 5.1 meters square. So this, all the units are transferred into one particular standard unit, that is your meter. So again, now we have the formula for total losses. Yesterday also we saw the total losses, wherein we have included the losses in the transformer. The losses in the transformer are due to convection and radiation, and those losses are 6.5 plus 6, that is convection and 12.5 s surface times theta. and the total loss is due to tubes only due to convection, so it is again 6.5, but you have some 35 degrees raise because of the tubes. We keep that margin, so it was 6.5 into 1.35 times theta. So usually x times theta we wrote. For tubes, your dimension we have wrote in the yesterday's class, x times st. For tank, if the surface area is st, so we can directly write the formula from the yesterday's class. We can also remember this for an easy recapitulation during the examination time. Total losses we can directly write down 12.5 st theta plus, yes, 8.8, and this is x st theta. X xt theta can be also represented by one particular this is the area of the tube. This is area of the tube, because basically this is the surface area of the tube. Losses already they have mentioned. They have mentioned the losses is 7 kilowatt. So kilowatt in terms of watt, if we write 7000, because 1 kilowatt is equal to 1000 watt, so we can write this 7000 is equal to 12.5. st we have calculated 5.1. okay, theta is given again. Theta is given, how much it is, 35 degrees Celsius, and you have this as 8.8. you have 80, again theta is given 35. From this particular equation, if you cross multiply and solve, you can get the value of 80. So the value of 80 here would be 15.6 meter square. So you got the value of 80. So what is basically 80? 80 is the area of tubes. So the total area of the tubes. Now what we want, the number of tubes it would require. So number of tubes it would require would depend upon the dissipating surface area of each tubes. So number of tubes it will require, number of tubes would depend upon dissipating surface area of each tube. Yesterday's derivation also we have seen that surface area is pi times diameter of the tube and length of the tube. So diameter of the tube, it is given in the problem. The diameter of the tube, if you clearly see the problem here, it is given diameter is 50. Diameter is, here you can see, diameter is 50 millimeter, and length I have taken 135 centimeter. So you have to convert this unit into a constant unit, that would be in meter. In meter, 1.35 would become, your length would become 1.35 meter, whereas your diameter is 50 millimeter. So you need to convert millimeter into meter. So your 1 millimeter, your 1 millimeter is how much? 1 millimeter is equal to 10 centimeter. 10 centimeter, that means 1 centimeter is equal to 0.1 point, that means 1 millimeter, sorry, 1 centimeter, 1 centimeter is equal to 10 millimeters. That means your 1 millimeter is equal to 0.1 centimeter, whereas here you have seen your 1 centimeter is equal to 10 power minus 2 meter. So if you have to convert this centimeter in millimeter into centimeter, so your 1 millimeter would be equal to 0.1 into 10 power minus 2 meter, because this is centimeter. Instead of centimeter I have written 10 power minus 2, and this is 0.1. So 0.1 will again be 10 power minus 1 and 10 power minus 2. So this is 10 power minus 3 meter. So here you have to directly 50 divided by 1000. So it would be 0.05 meter. Now you have to substitute these values here. This would be pi into 0.05 into 1.35, and the area would be, if we are calculating, this area would be equal to 2.212 meter square. 0.212 meter square. Now from this we have seen we have the the number of tubes required we can calculate from the formula area of the tubes and area of tubes and dissipating surface area of each tube. So now from this particular formula we can arrive at the number of tubes required. So the number of tubes required would be capital AT. Number of tubes required would be your capital AT by, see here, number of tubes required would be your capital AT by small at. So your capital AT we have calculated previously. So how much we have calculated capital AT? 15.6, and so it would be 15.6, and this we have calculated as 0.212. So total it is approximately getting 73.6, but we'll approximate it close to the nearest integer because we cannot take the value of a tube in fraction. So now one more important concept here in the problem is, it states that so we got the values for this particular thing. Now the thing is that how the arrangement of the tubes would look like. So there are things like how tubes are placed. Tubes can be placed 7 centimeter apart, they can be placed 7.5 centimeter apart. It depends upon the data. Here they have not mentioned, we can stop at this. But for example, if they had mentioned the tubes are placed 7.5 centimeter apart, then the number of tubes that can be placed along 110 centimeter and 60 centimeter are. So you have the dimension, you have the length and the width, because you have from this you got length of the, and the width you have got around 110 centimeter, and the length you have, this is your 60 centimeter, because previously also we have seen your length and your width. That means this is the total length, this is the length and breadth, this is your length, and we can say this is the breadth of, or we can say width of the tube. So what is that? We have considered this including the clearance factor. Now suppose each tube was placed, because tube would be placed across this point, across the length some tubes would be placed, across the breadth some tubes will be placed. For example, all the tubes are 7.5 centimeter apart. So how many tubes have to be placed in a length of 110? Tubes placed for length of 110 centimeter would be how much? 110 divided by 7.5. Similarly for width of 60 centimeter, it would be 60 divided by 7.5. So it comes around 15, that is this point 15, and this comes around how much? 8. So we can see if 15 and 8 tubes are provided, then the total number of tubes, so total number of tubes obviously would be 15 plus 8, that is 46. Since we have got 74 tubes are to be used to dissipate the heat, and additional row of, now see, we require only 46 tubes if this length is placed, but since we have calculated this 74, so we need to provide an extra protection for cooling. So for extra protection, if we are adding an additional row, if we are going for an additional row, because we are having this 74, if we are going for additional row, it would be 46 into 2, so it would be how much? It would be around 92, but we are only having 74, so it is the economics is 74. So what we do, we are getting here around 15, okay, here we are getting 8, so let's reduce it. Let's go for 13 here, let's go for around 6 will go, and let's see what happens. Now 19 into 2, this is 38, okay, and 38 twos are 76. Okay, two more tubes we can put. So what we can do here, we can put 13 tubes here, 13 tubes here. Okay, 13 down, 13 here, 13 here, 13. So this is 13 fours are 52, 6 here, 58, 6 here, 64. And we can put another we can put another tube of like, so we have left with 13 into 4 52. And if we are putting six tubes over there, so this is 12, so this would be your 464. And we can put another 64 we have arrived. Now we have another 12, so we can put another 6 here, another 6 here. So it would be 12, 12, 24, 24 plus 52, 52 plus 24, 76. So it would be very compact and very accurate, and it would be very economical also. We are not putting lesser number of tubes, and we are not putting too large a number. We are putting just 74 we calculated, we are going for 76. Similarly, one more problem we will be solving, will be taking up. And already I am making precise video, short videos, because I am not going for a larger length. I want you people to follow. If you have any problem, any doubt, in the comment section you can please tell me, and I'll try to inculcate any mistakes if I have happened. Please see to it. And please stay safe, please stay indoors, study hard, prepare well. Now this is the best time, and try to form some habit, because 21 days is the time when a good habit is formed. If some of you might have picked up some wrong habits during the school or college, you try to quit that, because now you are living with parents. Now this is the best time, and think this time as a blessing from disguise. And together we can fight and eradicate the evil corona from our country, India. Thank you very much.